Hi, good morning. How's everyone doing?
Good morning.
Hi.
Good morning.
Good morning, Professor.
Again, just a reminder, your video is automatically turned off when you come to the meeting. Feel free to turn it on and help us be more focused and engaged. You can always turn it off whenever you need to. Okay. All right. So we're going to do one example problem, which is also one of your homework problem on the free fall of motion. And it's not just free fall, it's also a catch problem, like two objects meet each other. So that's one of the very classic problems you will see quite a lot in this section. And after that, we're going to do a little bit of math on vectors in two different directions, and that will help us answer questions of motion in 2D, right? Not only you're moving just horizontally and vertically, but you're moving with both a horizontal and vertical component. All right, so let's take a look at this question. Notice that every time you will have different numbers. So these numbers are just at one time the numbers pop up. Your numbers will be slightly different than this. So we have a small object, begins a free fall from a height of 29 meters. After 1.1 seconds, a second object is launched vertically upward from the ground with the initial velocity of 35 meters per second. So at what height above the ground will the two objects first meet? So this is a classic meet and catch problem. I want to be able to model how we solve problems and how do you convert a word problem to kinematics equations. Okay, so first of all, we want to draw a picture, right? When we have a word problem, drawing a picture helps us visualize and translate that information into kinematics equations. So let's draw a picture to help us visualize. So we have a small object from a height. So let me go ahead and I'm gonna draw. So this is 0, this is at 29 meters. Okay, and an object is released from the height. Okay, so that's the information we're given. After 1.1 second, another small object is launched from the ground. So another one was here. It's going with a velocity that is 35 meters per second square, but that is after 1.1 seconds. Okay, so which means eventually they will meet, and let's just assume they meet somewhere here. That's when they meet. I want to know what is this height. Okay, so if the total time it takes for this object to travel from here to here is time t, and what is the time it takes for this object to go from the ground to this position? What is this time? So if this is represented by t, this time is represented by what? Do they all travel with the same amount of time? T minus 1.1, very good, yes. T minus 1.1, because if this object had traveled t, this one is launched after the other one. So the total time for the second one to travel is less. How much less is 1.1 second less, right? So this is t minus 1.1 second. Okay, so here I have labeled some of my quantities, and you can see how I translated this word problem onto my picture. Okay. All right, now I want to use kinematics equations, and because I have two different objects here, we want to be able to do our labels very carefully because we don't want it to mix different information. So I'm going to show how I labeled each of the quantities. So don't worry that you can do it slowly to avoid making mistakes. What does 29 represent? I got a question. 29 represents this object is released from this height, okay, 29 meters. Okay, So we will do all the kinematics quantities list them for object 1, which is this object 2, which is this object separately. So let's do object 1. I want you guys to help me, right? Okay. Object 1, and you can see that implicitly I have already defined my positive direction upward as my positive direction. You do not have to define that way, but once you define a positive direction, all your labels has to be consistent with that. So let me ask you, what is the initial position of object 1? So you can see when you have multiple objects, you may need to use 2 subscripts to differentiate. So this is the object 1 and initial position, okay? So I'm not gonna say not because I wanna use initial and final. When I have 2 objects, it's easier to do initial and final. So, and this is in the vertical direction, I'm gonna say the Y as in to represent position. So this one is asking you, what is the initial position of object 1? Can you guys tell me?
Would it be 29?
29 meters, excellent. And when they meet, what is the final position of object 1? This is when they meet.
Is it 29 minus h?
It's the initial position, not the total time it travels. So I read 29 here, that's my initial position, and I read h here, that will be my final position. So 29h would be the total distance it traveled. It represents something else. So I will just write h here, and h is what I want to solve for, right? I don't know what this is, I want to solve for it. Excellent. So what is the initial velocity of object 1? It's being released.
Initial velocity is 0.
Yes, very good. Okay, so I'm going to list all of these, and the time it travels, I don't know. I'm going to say it takes total time of t to travel. So these are the quantities I'm going to label for my object 1. And I'm going to now label my object 2. Okay, so I would say, what is the initial position of my object 2? Y represent position. Initial is indicated by I, little I subscript, and this is object 2. Where is object 2 at the beginning?
0 meters.
0, launched from the ground, excellent, so that's 0. And the final position of object 2, when they meet,
H.
is also h, and then see they share this common variable. That's the variable I want to solve for. And what is the initial velocity of object 2?
$35 meters per
35.
second.
35, excellent. All right, and how much time the object 2 has to travel? It's t minus 1.1 seconds that we have already established here. Okay, so I'm just going to write it out here. Okay, now I have everything. You can see that when they meet, so this language tell me they occupy the same position. They have the same position, which means y1 final is equal to y2 final equals h. They have the same position, final position, right? Okay, so now let me use, okay, and this is what kind of physics do we use? So I have labeled my quantities, draw the picture, and I think about, okay, I need to choose an equation to use. What equation do I choose? Well, what kind of physics do you have? You have a free fall motion, free fall type of motion, and we know free fall is a particular special type of constant acceleration where acceleration is pointing down that is always 9.8 meters per second squared, right? Little g. And here, since I have defined upward is my positive direction, I'm going to label my acceleration as negative because acceleration is pointing down. So this A is shared by both objects. So I do not need to label A1 or A2. They have the same acceleration, right? So so for constant acceleration, I know, and now you can choose your equation after you figure out what physics is involved. So we have two equations, V equals V naught plus AT, X equals X naught plus V naught T plus 1/2 AT squared. So take a look at this information. Which equation do you think I should try first?
The second one.
Yeah, very good. Because I was given information about they occupy the same position. So I certainly should use this equation because it contains information about the position, right? So that's how I choose an equation. It's not simply randomly plugging into any equations, but I pick them out with a purpose. So I'm going to use this equation. I can use it for object 1 and I use it for object 2. Now, if I use it for object 1, this is the final position, right? And the final position is at H is equal to initial position. Now you can just plug in these things that you have laid out for yourself, right? Initial position is 29 meters. And you don't always have to write your units. If they're all kept with the same unit, you can just leave out the unit for now. Initial velocity is 0. I'm going to plug in 0 here. You can see that becomes 0. So I'm not going to need to write this term. And this is my last term. So it's 1/2 9.8 negative T squared. Okay, that's the first object. Second object, the same thing, same height. Initial position is 0. Okay, so this first term is 0. Second term is going to be initial velocity, and you have a positive initial velocity launched upward, right? 35. I'm going to say 35 times the time for the second object. Be very careful. The time for the second object is going to be T minus 1.1, not the same T. So here I really need to replace the time with T minus 1.1. Okay, so the T here is just a generic time. I used this variable T to represent the total time it takes, but to make the equation consistent, I need to use this variable T minus 1.1 because if this represents a certain amount of time, I need this to represent a smaller amount of time. So be very careful. If you here put T here, then you would have made a mistake, indicating that object 1 and 2 travel with the same amount of time. Okay, last term is again 1/2 negative 9.8 T minus 1.1 squared. Okay, so here we just need to solve for H, right? You can see that I have two equations, two unknowns. I can solve for time, I can solve for H. So make it 1 is equal to 2 because it's the same height, right? Same H. And you'll end up with some equation looks like this. And solve for your time. Okay, so the time, you solve for the time, you will get this number, 1.6 seconds. And you can plug in into any of these two equations. You can plug in here, or you can plug in here, doesn't matter. That will give you the height you're looking for. And the question is asking for the height. Okay, so that's it. That gives you the final answer. Any questions about the process of how to solve this problem? Any questions? Yeah, I set both equations to each other because they occupy the same final position, right? It's both H. So I really do H is equal to this, H is equal to that to show how we did it for object 1 and 2. And when you're really familiar with it, you might just directly make this equal to that. You don't even have to go through the step of setting them to each of them to H first. Okay, so there are some questions. Can you explain how I know how you knew which equation to use? I use this equation because the problem gave me information about the two objects meet. So when they meet, meaning that they have the same position. So that is information that you were given. You want to use that information. So how do you use information about position? Is you need to choose a equation that contains position, right? This is about velocity. So that's why I know how to choose this equation. How do I get t minus 1.1? Because if the time it takes for the first object when it's released to when this object meet another object, if that is t, let's say t is 3 seconds, okay? But the second object is launched after the first object. So it's about 1 second later. So the total time the second object travels upward will be less than the total time the first object traveled. That's why it's t minus 1.1. The time it takes for the second object to travel is less. So that's why I put t minus 1.1 there. So t originally in the equation is a variable, is a generic variable. But once you put it in your equation and plug in your quantities, this represents a certain amount of time. Imagine if this is 3 seconds, right? Then the second ball object must have traveled 3 minus 1 second is 1.9 seconds. It's not also 3 seconds. Okay. Thank you all for the questions. Any other more questions coming up? Okay. All right, so if there are no more extra questions, let's move on to do vectors in 2 different directions. So I'm gonna go here and share my slides so I could animate my slides here. Okay, change gears a little bit. We talked about how to represent vectors. We need to give a magnitude. We also need to give a direction. Sometimes a vector is in 2 different directions, for example, x and y, and you can see that we use this unit vector I hat and j hat. This symbol represents the direction. So you can either write x hat or you can write I hat. That all simply meaning it is the horizontal direction. Y hat or j hat represent the vertical direction. It's simply just a writing, showing people in that direction. So for example, if I'm going to say a vector is 4 I hat, what does that mean? The 4 units of the magnitude in the x direction, right? So A will be represented 4 I hat. You can see it represented by this red arrow pointing in the positive horizontal direction. So horizontally going 4 units. And if I want to draw 3j hat, what do I do? 3 units in the y direction, right? So 3j hat. And when you need to multiply these 2 vectors together, you get another third vector. That's 4 I hat plus 3j hat. So how do you draw C? How do I draw C vector? What do you think? Anybody would like to?
We could just go for it, like if we had this labeled, we could go x over 4 and then up 3, and then draw that line from the origin.
Very good. It's like if you were traveling going east for 4 miles and you travel north again for 3 miles and you're finally here, that is your final position. Excellent. So that will be our final vector. And you can see this follows head to tail method or the other method that the A plus B as in vector addition does give you C, right? Okay, so that would be vector C, and vector C has a length of 5 because this is a triangle. Pythagorean theorem 3 and 4, you give 5 on the hypotenuse. So it also makes an angle about 36.9 degrees, about 37 degrees above the horizontal direction. So you can either tell people, oh, my position, if you need to tell people your position, say, oh, I'm at 4 miles east and 3 miles north of where I started. Or you can tell people I'm north of east 36 degrees and I'm 5 miles away from my home. So both of those give you the same information about your position. So sometimes you see people represent the vector using magnitude and direction, as in how many degrees you are with respect to the x-axis. Okay, so 2 different representations, and we should know what it means. They all tell you the same vector. So if this generic vector is A as an X component, B in the Y component, so you can write it using AI plus BJ, AI hat plus BJ hat. The magnitude of A is square root of A squared plus B squared, and the angle it makes with the X direction is the tangent of theta is B over A. Okay, so all of that. Any questions here? Okay. So splitting vector into these components sometimes make our calculation easier. So you can see adding A and B in 2 different directions, right? You can use a nice ruler and draw your overall, the addition, and well, how do you calculate the magnitude? When it's a triangle, when it's a right triangle, it's easy, but sometimes it's an irregular shape, it might be a little bit harder. But if we were able to represent our vector using the X component, Y component, and then the vector addition becomes just like algebra. So for example, take a look at this. If A has 2 components in the X direction and 3 components in the Y, B has 4 components in the X and -1 component in the Y. If I need to add A and B together, what do I get? So the final vector of A plus B has how many components in the X direction? If A has 6, yes, very good. You can see that once everything is in the same direction, you can simply just add them up like numbers instead of vectors, because their vectors are already in the same direction. The direction idea is already taken care of. You can just simply add them up, right? So it becomes 6 and 4 plus, and 3 plus -1 is 2. So the overall addition of A plus B becomes 6i hat plus 2j hat. Okay, so that makes the vector addition quite simple. So let's take a look at this question. You have now 3 vectors. So even we are seeing the advantage of using addition by components because there are now 3, right? If you were doing the head to tail, you need to add all 3, and that might be very difficult. So S is A plus B plus C. Now, what is the value of S as X? The X component of S. Which one of these do you think is correct? I'm going to go ahead and let you guys vote on this. I don't know if you can see this clearly. You can see that the A, right, is 3 units to the right and 1 unit down. B is 3 units to the left and 3 units down. C is 3 units to the left. So if that helps. Okay, so 10 more seconds. If you haven't voted already, please put in your vote. Okay, any last minute vote? Okay, I'm gonna go ahead and end our poll, okay? Let's take a look at our results. Here is our results. All right. Okay, so let's see how we're going to be able to answer this question, right? If we didn't know how to break it down into components, we'll probably start trying to add them up, head to tail. But now I indicated each of them have their component in X, Y. So how do we find the overall X component of S? Anybody would like to share their thoughts with us?
Since you're talking in terms of X components, you look at, I looked at the horizontal axis, so then that's where you determine. So if it's 3 units to the right, then it's positive, and then it's 3 units to the left, it's negative. And then when you add them together, you get -3.
Oh, okay, very good. There will be 3 units here. Okay, I'm using I don't think it'll let me write. So this is just 3 positive, and this is -3 from the B, and another -3 from C. So you add them all up and you get -3 overall. Yes, very good, excellent. So the X component of S will be just -3. Very good. Now, here's another question. I have 2 vectors. Each of them are given by the components. Okay, so AX is 1 unit positive, 1 unit positive in the Y direction. BX has -2 units in the positive, -2 units in the X direction and +2 units in the Y direction. What is the overall direction for A minus B as indicated by 4 different choices? So does you think this arrow A represent S, or B represent S, or C or D? Now this one is slightly more complicated than the previous question. You can take a screenshot and I'll let you have a discussion with others for about a couple minutes, okay? So whenever you're ready, you can join the breakout rooms invitation, and we will talk about this together when you come back. Make sure you record the question when you go. Okay, so as you come back, please go ahead and enter your votes for this question, please. Okay, let's run for another 10 seconds. Okay, all right, let's go ahead and end this and let's take a look. All right, so here is what the answer distributions looks like. Looks like we are have a big agreement on the choice D, right? So S is equal to A minus B. You can see that here we have two different vectors. AX is 1, right? BX is -2. So if you use A minus B, what is the X component of S? What is SX? It's going to be a number. What number would that be?
3.
It would just be 3. Very good. Now AY and BY, what would be the Y component of S?
-1.
It'll be -1. So look at the X and Y coordinates. I have a +3 and a -1. Yes, indeed, it was represented by choice D. Very good. All right. Okay, so just 1 second. We go to or back to my slides. All right, so if the information were given to you by a magnitude and an angle, as I indicated to you earlier, can you guys see my screen?
Yes.
Okay, vector addition by components. So for example, if the information were given to you as A is 6 magnitude, 120 degrees, with respect to the positive X direction, and 4 for the magnitude of B and 210 degrees, then I want to find C, right? If the information were given to you this way, then you will find your X component for A and B first and your Y component for A and B and add them together, because the X component is simply A times cosine theta, right? So if you draw your little vector here, A, this is theta. So it's going to be the X component is AX, which is A cosine theta. So you calculate that. AY will be A sine theta, and you calculate that. And the same thing for BX and BY. Once you find these components first, you can do the vector addition. So -3 plus -3.5 is -6.5. So that's your A, and your B will be 3.2. And you can find your overall magnitude if you wish, but you can simply leave your answer as here. That's your overall for C. So I want to show really quickly an example where vector addition makes it a little bit easier to do. So for example, you have a boat. Originally is located at 5I4J. So where is 5I4J? Is right here. It's 5 to the positive X direction and 4 upward. So this is where the boat was. And then the boat sails 60 degrees north of east. So north of east represent from the east direction, you go up 60 degrees. So 60 degrees is here, north of east, represented by the blue arrow. Okay, that's the final position. So it went for 2 meters per second for 5 seconds. So continue to go straight in the blue arrow and then until it reaches its final position. So what is the boat final position? You can see the final position is represented by the red arrow right here. So this will be very hard if you were to do this using the graph representation, but it will be very easy if you break it down into components, right? So the initial position is represented by 5i4j, and velocity is at a degree, 60 degrees. But in terms of the x and y component, I can do 2 cosine theta for x component and 2 sine theta for the y component, right? So my velocity is also in terms of x and y component. The final position will be the initial position plus the velocity. Okay, and you can also see that head to tail method showing the final position is your initial position plus the overall change in position, which is your displacement in the same direction as your velocity, right? So these two vectors should add up together to give you the final position. And once you break it down into components, the addition becomes very simple. You add the 5i and the 5i together, you add the 4j and the 5 square root of 3j together. So that's your final position. This is a quick example to show when you do it component by component, sometimes it's really easy to solve problem that way. All right, next with this knowledge of motion in vectors in 2 different directions, we're ready to analyze motion in 2 different dimensions. So 2 different dimensions, like if you throw some object and it goes in the trajectory, a parabolic trajectory in air, that's considered a motion in 2 different directions, 2D. I want to start out with a clicker question, sort of just get our intuition on these type of problems. Now, for example, if you have sort of a train cart going with a constant velocity forward, and you're standing at the center of the car and throwing a ball up and down, right? So don't consider air resistance. Where do you think the ball will land? So this is sort of another, so whether it's forward of the center of the car or at the center or backwards, right? If I ask you another question, if I say, if you stand at the center of the train cart and throw a ball up and down, will you always be able to catch it? What would you say? Can you always catch a ball if you throw it up and down,
As long as the train keeps moving at the same velocity, which it is in this case, then yeah, you'll be able to catch it.
Yeah, as long as the train is continue to move with that same constant velocity, you can always catch it. This is just like, oh, if we all have the experience traveling on the bus, or we are in the airplane. Of course, I can throw a ball up and down, always catch it. The ball will always land in my hand, as long as the plane is not accelerating or decelerates. So going back to this question, if I asked you, where would the ball land, what would you say? Here, you are at the center of the car. So if you think you'll catch the ball, would the ball always go back to the center of the car?
Yes.
Yes, it would, right? It would not be in front of you or behind you. If it's in front of you or behind you, then you cannot catch it, but it's always going back to the same position as you are, so therefore you can always catch it. So what is about the motion of the ball? You know that the ball must be traveling together with you with that same constant velocity forward at the same time as it's going up and down. So here we can show sort of a demonstration of what we just talked about using this demo. Let's take a look at this demo.
Good grammar and spelling are important, but if you want to write essays that inspire.
So let's look at this demo. It goes kind of quick, but they repeat it several times. Okay, let's look at it again. So what this one is doing, I'm gonna explain a little bit what we're seeing is you have a little cart and it has a device in it with a spring, it can launch a ball upward. So you can see as it moved through the tunnel and the ball also moved to the other side of the tunnel and land back at the catcher where it landed. Okay, so you can see that it still will be able to catch it on the other side, showing that the ball is moving together with the horizontal velocity of the ball is moving together with respect to the card. So that's not affected. So let's go back to our slides. So if we were to draw a little vectors to show the different velocities, you can see the card, of course, is moving with the velocity v, and the ball, while it's being launched upward, it still have the same velocity v, right? So what happens is the motion of the ball in the horizontal direction is unaffected by the motion of the ball in the y direction. So that's why when you go to the right-hand side of the tunnel, the ball simply just reverses its direction in the y direction. It's going upward first and then going downward. Okay. And you can set percent, it still can catch up with your cart. So so that is also the method we will use when we analyze motion in 2D, is we'll look at the horizontal motion and the vertical motion separately because they are independent of each other. The vertical motion will not affect your motion in the x direction, right? So the B to the original question was correct. So when you say, before I show that picture, I would say, okay, when you are standing on the center of the car, of the train, and you throw a ball up and down, what is the trajectory of the ball looks to you? Does it just look like a straight line up and down, up and down?
Yes.
Yes, it is, just up and down, up and down. What about someone else on the train? What do you think they see the trajectory of the ball?
Up and down, up and down.
Parabola, inverted.
Yes, exactly. Yes. So if someone is on the train, they also see the ball up and down, just like if you are on the ground with someone, they will see you throwing something up and down, because you both have the same horizontal velocity. You, someone else on the train, or the ball, they all have the same horizontal velocity. So you will not be able to perceive that horizontal velocity. But for someone standing on the ground, looking at you, you are going horizontally forward. But if you look at the ball would be going forward and up and down at the same time. So if you put those two motions together, for someone standing on the ground, this person here, they will look at the ball going as a parabola, right? A curve up and a curve down, and another curve up and curve down. So that is sort of the addition of the motion in the x and y component together. So that is the difference of so this is also something we call as a frame of reference, different depending on your own reference. If you are on Earth, that's your frame of reference. If you're on a moving train or moving car, then you may have a different frame of reference. So the motion of other objects will look different to you depending on where you are, depending on what your frame of reference is. So we all have that experience, right? If you are, if two cars are running side by side with the same velocity, and you look at the other car, it as if they were not moving because they're keeping up with you. But if you have another car passing by you in the opposite direction, we feel like they're just going by like shoosh, super fast, because you have yourself going one way, they go the other. So the relative velocities of the other car is way faster. If you are going 50 miles one way, they're going 50 miles per hour the other way, then relative to you, it's as if they're going 100 miles per hour. So that looks very fast. So your motion will appear different depending on the frame of reference. But that we're not going to do frame of reference in this class, but it's good to simply mention that idea. All right, so we'll continue with the discussion of 2D. We'll look at more questions and examples on Friday. And so that's all we have for you today. Have a good rest of the day. I will see you guys next time.
Thank you, Professor.
Thank you. Bye,
Thank you,
everyone.
Professor. Have a good day.
Professor,
good day
do you have
yourself.
an answer? Do
Thank
you have
Have
an
a good day
answer for
yourself.
that question we did together with the vectors? I mean, sorry, not with the vectors, with the velocities and the meat question.
Oh, which question? I'm gonna scroll upward. You can tell me where to stop.
It was the one that one ball was at 29 meters per second and it was dropped. I mean, at 29 meters and it was dropped, and the other
Oh,
was thrown
yeah.
at 35 meters a second.
Yes, I do have a final solution here. It's a 16.5 meters,
Oh, okay, cool. Thank you.
but your numbers will be different.
Yeah,
Okay.
slightly depending on rounding.
Yeah.
Cool.
Okay.
Thank you.
Sure.
Hi, Professor. Just a quick question.
Yeah.
For the homework, for homework 2,
Uh-huh.
which chapters and sections like are we supposed to? Well, not supposed to, but which chapters and sections do we read? So like it would like help us on the homework.
Oh, homework 2 is 1D motion. So, so almost homework is always a little bit behind. So homework 2 is under week 2 folder, but it's about week
Okay.
1 stuff. So if you go to the
I don't know if it's just me, but I can't hear you on my end, Professor.
Yeah, I think you cut off.
I'll see you guys next time. Okay, bye-bye.